So many buttons. There. Is that working? Can you see me? Can you hear me?
I can see you and hear you, and somehow you always get louder between pre-show and actual show.
Really? I do that on purpose,
It hurts.
I keep yanking on my headphones and sort of pulls out of my ear, and I think I'm going to break them. Anyway, not your problem. Not the viewer's problem. Let's just say I need a longer headphone cable or a computer that's
I,
closer to
I
me.
wish I wish that Bluetooth didn't lag and create interference. 'Cause I love my Bluetooth headset, but they just don't work for Hangouts.
Yeah, I feel exactly the same way. Like if that technology worked, I would use it for everything, but it
Yeah,
fails me often enough that I can't depend on it. It sucks.
right.
Anyway, hey everybody, my name's Fraser Cain. I'm the publisher of Universe Today, and with me here is Dr. Pamela Gay, and we are going to make an astronomy cast for you. You're going to watch it happen, so enjoy. um, so yeah, if you have no idea what the hell it is that you just stumbled into, this is going to be a live recording of Astronomy Cast, episode 371, the Eddington Eclipse experiment. I apologize, I'm a little sore throaty, a little allergic-y. It's that time. Spring.
We're
Anyway,
sorry.
um, and so that'll take us about half an hour, and then we will stick around for as long as we can and answer your questions about space and astronomy. Pamela, you are home from the road.
I am. I was gone for a little less than a week to go to the Lunar and Planetary Sciences Conference down in Houston, Texas, and yeah, so you have me in high res this week, unlike last week.
Yeah, exactly. And of course, you can interact with us just using the Q&A app. So if you're watching the show and you want to interact with us, you can click somewhere on the screen and a window will pop up and things will happen. So feel free to enjoy that. And just to show that it does work, I'm going to say hello to a bunch of people. I'm going to say hi to Tony Lynch and Jim Meeker and James Gibbs and Guido Bibra and Illit Avron and Helge Bjorkog and Michael Jobin and Gazelle Sabarin and Thomas Traniker and Nancy Graziano and Peter Waldman and others who will show up later on. So hello, all of you. Welcome to Astronomy Cast. Enjoy. Anything you want to talk about before we proceed?
No.
No? Okay. All right. I'm sure you'll have things to say in the show itself.
Yes,
Okay.
that I
All right.
have.
All right. Well, then let's do that. Then I'm just going to start hovering over my record button.
Okay, I'll do the same. I am pressing record. It's recording, mono, everything worked.
Everything
Go
works for
figure.
me too.
Hi, Preston.
Hello, Preston. Enjoy this astronomy cast that we are about to make for you. Here we go. Astronomy Cast, episode 371, the Eddington Eclipse Experiment. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing great. I apologize. I'm a little throaty today. It's allergy season, and I don't know. I've got a bunch of pollen clogged in my throat, I think.
That is sadness.
Yes, but I'll tough through it. Do you have some kind of announcement, some news about the
I
Hangout-a-thon?
I do. So we are gearing up for the 2015 CosmoQuest Hangout-a-thon. It will be April 25, 26. We now have the event pages up on Google, and I'm, for one, very grateful that we can now record 8 hours at a time. And we're partnered up with the Astronomers Without Borders, Global Astronomy Month, Global Star Party. So we will be bringing you live coverage of star parties around the world following the night as it passes from nation to nation.
How cool is that? It just gets bigger and more insane every year, and we watch you go crazier online, 36 straight hours of Pamela broadcasting.
Yeah, if there was an easier way to fund myself, I would, but this is the most reliable Yeah, I
Yeah.
trust you guys to do what's right more than I trust referees who may not have actually read my grant proposal to do what's right.
Right. Yeah, so the event page is already set up, and so if you're listening to this, how could people navigate to the event page to click yes, so that they then get all of the updates and recommendations that will go into your calendar? Where
Um,
do
so we are plus CosmoQuest on Google Plus. That sounds
Mhm.
redundant. And just look up all of our events. They should be the most recent 4 posts on our feed. And I will be putting all those links on our Google Hangout page. And that's over on CosmoQuest. And I, of course, have forgotten the bit.ly link in the time it takes me to
Mm.
open up and get to the show.
We'll get that next week. We still have a little time.
We do.
All right. Well, let's get cracking then. At the turn of the 20th century, Einstein's theory of relativity stunned the physics world, but the experimental evidence needed to be found. And so, in 1919, another respected astronomer, Arthur Eddington, observed the deflection of stars by the gravity of the sun during a solar eclipse. Here is the story of that famous experiment. So we're continuing our sort of series on experiments, and they all seem to be hovering around relativity, which is kind of great. Like, Einstein was right, as we've said in a previous episode, and these are the experiments that showed that he was right. Now, this one, of course, is great because Arthur Eddington looked exactly like David Tennant, as I recall.
So I'm not the only one who found that while preparing for the show. Yeah, there was
Well, he did a show.
apparently the
A
BBC
documentary.
show.
Yeah,
Yes.
did a dramatization of
Have
the
you
Arthur.
seen it?
Yes, yeah.
I love you with hate or hate you with love. I'm not sure which. I tried frantically to find that show because it's two awesome people. David Tennant, how do you say his last name?
Circus.
Yes. Gollum.
Yes.
They did a show where they played David Tennant was Eddington, and Andy of Gollum fame was Einstein, and it was apparently quite excellent and
It
is
was
impossible to
wonderful.
get in the U.S.
Yeah, I guess as a Canadian, we get access to the BBC stuff, and I remember watching it like a long time ago. Like, it must have been six.
Came out in 2008, and HBO ran it in 2010, but I don't have HBO,
Yeah,
so.
there's got to be some place on the internet. So, email Pamela with a link to where she can find it, and she'll get a chance to watch it as well. But yeah, no, absolutely terrific. And so it's great to have it dramatized. And so I saw this just wonderful relationship with Eddington and Einstein as they sort of, Eddington went out and helped find the experimental evidence to support these really revolutionary theories. So what happened in reality?
So from what I've been able to piece together, the two of them did actually work together on this insofar as Eddington was very much a I want to figure things out by the books kind of man. He did do some stupid things now and then. He did not believe in white dwarfs. It was a belief system. He and Chandrasekhar fought for years and years and years. But at the same time, he was also someone that was very interested in trying to figure out things like why does the sun work? Why do we see what we see? And he was the person who figured out why actually the sun has been glowing for longer than fuels like coal would allow. But one of the other things that just kind of itched at the back of his brain as this constant annoyance was our inability to explain the orbit of the planet Mercury. It was off by just enough that you couldn't wipe it away by saying it was observational error. And when Einstein started publishing his theories, Eddington engaged him in conversation, basically trying to understand what are all of the observational problems this is now going to explain away. And once he wrapped his head around the idea of relativity, he looked up when is the next eclipse that one can get to that is a full eclipse and long enough to set up cameras of the time. And it was the 1919 eclipse that passed over Africa and the island of Principia off the coast of Africa, which is where Eddington went.
That's right. And so the experiment that he was trying to do here was as predicted by Einstein, I guess gravitational masses will be warping space-time, and so the sun should warp the light that's moving towards us, but that's a really hard thing to test because the sun is so bright, and so the only time you're going to be able to see that is during an eclipse. So what was sort of the experiment setup that they were looking to do?
Well, conveniently, the sun was affecting the light from the Hyades cluster, a nearby cluster of stars that's many dozen million years old. Actually, I think it's over 200 million years old. And these stars are spread out a fair amount. They're sort of scattered all over the head of Taurus the Bull. And the sunlight, depending on how far the sun was from the light of a given star, would bend the positions that the stars appeared to be at, because the light, rather than shining straight towards us, well, it would get bent. So the light we would normally see would get bent out of our field of view, and the light that would normally shoot above or below or beside the planet Earth would instead get bent to actually reach us here on the planet Earth. This bending changes the apparent positions of the stars. Now, Newton's theory of gravity also predicted that gravity would have the ability to bend light, but because Einstein's theory didn't actually bend space-time, his theory was off by an entire factor of 2.
So the measurements that Eddington was trying to make of the positions of the stars next to the sun would show whether Newton's ideas about how this should work or how Einstein should work, which one was more accurate. And so the precision of the experiment was really important. Now, I know that while Eddington was in Africa, other teams were in South America because the eclipse was going to do this big long path, right? And so this was part of it as well, was they wanted to test this out from different positions on the Earth as well.
And so we had astronomers that were in Brazil catching one part of the eclipse path. We had Eddington on Principia, which is actually an island off the coast of Africa. And they were all basically doing if enough of us look up, someone's got to be without cloud cover. And this actually meant that the observations were more complex than one might wish. So you have the problem that when you look at something like a cluster of stars, you're capturing that light through an optical system that may have all sorts of distortions in it. And we've done several different shows on this. So you have to, as best you can, use the exact same optics and the same optical alignment, but you can't always do that. So they did the best they could. They did fancy plate solutions to try and correct for everything that was wrong with their optics. And they took images first when the Hyades cluster was in the night sky, far from the sun, and then they captured pictures of it during essentially the daylight, but during an eclipsed daylight moment. And in 1919, photographic technology wasn't exactly what it was today, so they're in a situation where they're trying to not destroy their optics because, well, the sun's corona is still there. It's not entirely dark. If you've experienced an eclipse, as many of you experienced on Friday, there's still a whole lot of daylight to deal with. And so their initial measurements weren't great, but they were good enough.
They were good enough. I mean, if I understand, there was a lot of controversy after they even made those calculations. I think if in the show, which is the way I'm going to base all of this, television taught me so much. But in the show, it was a slam. We've seen it. There it is in the telescope. Einstein was right. Have you got this, Einstein? So, but if I think, it was photographic plates. They brought them back. They had to study them. And there was enough sort of discrepancy in the way they did their calculations that a lot of astronomers weren't convinced.
And it was the basic problem of you're trying to take a photo very quickly. You've pretty much got a shot. And then you're making all of the measurements by hand on a system where all sorts of distortions could have come into play at various steps. So there's actually pictures on the internet that we'll try to find to put up in our show notes of the photographic evidence that Eddington took, and you can see the little marks identifying which of the stars are measuring, where the sun has essentially been blocked out by the moon. And there's not a whole lot of stars to go by, and they're not all snuggled right up next to the sun, so the amount of deflection we're looking at is the amount of a few periods of newsprint on the glass plate. It's not a lot to work with. And there was probably a whole lot of confirmation bias involved in Eddington's discovery. But the thing was, even if his initial results were, for lack of a better phrase, kind of crap, they got people thinking in the right direction. Had he come out and said, "No, Einstein is wrong," as so many cranks wish he had, there might not have been all the follow-up observations that were made. Instead, thanks to confirmation bias and the determination that the results would be correct, there was, first of all, cover stories and things like the London Times. And there was experiment after experiment after experiment knocking down the error and showing that while those initial results had a lot of error, had systematic bias, had confirmation bias that confirmed Einstein's theory, well, that confirmation bias was based in luck but led to the actual correct answer.
Well, and the other observations that were done in Brazil gave more evidence towards the Newtonian findings. So you could see why there was a lot of controversy, but still it was, and apparently like 1979 they did a lot more research and used modern computers, modern-ish Apollo era computers to reanalyze the data and got a much better result out of it.
Well, and luckily there are eclipses on a regular basis, so we didn't actually have to wait all the way up until 1973, which is lucky because now you're starting to get into things that happen in our lifetime. But in 1922, Lick Observatory was able to have its astronomers make a series of observations that agreed with the 1919, admittedly biased and highly errored results, and confirmed, yes, this does appear to be true. And it's been major eclipse after major eclipse since then where we've continued to improve our results.
Very cool. So, I mean, how did it kind of go after, with Eddington's work? How did this sort of affect his relationship with relativity as a theory and sort of the thinking and the science that he did? As you said, he was the person who figured out how the sun works.
Right.
And a big chunk of that is relativity, right?
No.
In that the sun is, I just think of it in terms of like that there's like the quantum processes that are going on in the sun. A lot of this is all connected.
No.
Now I sound like a woo-woo Deepak Chopra, don't I?
So Eddington was someone who was deeply passionate about understanding the observable universe and trying to piece together enigmas. And the sun was an enigma. When he started doing his research at the turn of the last century, people couldn't figure out how to bring the geologic record and the solar record together because the geologic record said Earth is older than the sun should have existed, even if we're going with the few thousand-year model, folks. And that's kind of depressing to think about, but they were trying to figure out how long the sun had been burning based on observed output and the most efficient energy sources we have on Earth, which are things like coal. And the sun as a coal-burning object just couldn't have lasted that long. And it was Eddington who sat down and started working through the quantum mechanics, which is in absolutely no way unified with general relativity. We haven't got there yet.
Still haven't unified those together.
Right. So he was deeply engaged in trying to piece things together looking at nuclear processes, looking at the results coming out of many other different individuals. There's J.J. Thomson's work that just got us to start thinking about things in quantized ways, and so many other people, and we're going to get to these in future episodes. But there were other enigmas out there that were bothering Eddington as they bothered so many other scientists, and Mercury's orbit was one of them, and being able to use the theory of relativity to start erasing these enigmas was a powerful thing, that he was in a position to go out and say, yeah, this theory actually works. But when it comes to his work with the sun, this was just a side foray into a different part of science. But what was important is we were able to go from, light gets bent, we know that from Newton, light gets bent more, we know that from Einstein, to now we know that there's gravitational lensing that we can use to see multiple replays of the same quasar as the light takes multiple journeys to reach us. We can use it to detect dark matter because gravitational lensing, dark matter that we can't see any other way bends light as it passes through the universe, and we can basically figure out from all of those bends where the dark matter has to be. Eddington's observations were the first step in a revolution in how we understand the path of light, and it's gotten us all sorts of different places.
So, we discussed this in that episode about Einstein being right, and we sort of talked about all the different kinds of observational tests. Some were done very early, like this one. This was really one of the big first observational tests. The precession of Mercury was the other one, but some have still yet to be done, even to this day, right? Some of the like the direct observation of gravitational waves has still yet to be done.
Right. So we're still missing gravitational waves, and it's been a steady progress. Einstein's theory of relativity started out from a place of we don't get Mercury. Oh, wait, now we get Mercury. To solid predictions where one of the quotes I found was Einstein famously made the quip, "Then I would feel sorry for the dear Lord. The theory is correct anyways," was his response to Dyson on how we'd feel if Eddington didn't observe the correct amount of bending of light.
Yeah, God is messing up moving the light race because I'm right, not God.
Exactly. So we went from he solved the problem with Mercury, done, out the door, to predicting how the light would be bent, and they had the technology at the time, albeit with a lot of errors, to prove that his idea for a test actually confirmed his results. Then there were the time dilation issues, which we needed more precise clocks. But atomic clocks came along, jet planes came along, and we've proven the ideas behind time dilation. The muon, which we figured out how to detect, proves the idea of time dilation as well with its journey from the upper atmosphere to the Earth without destroying itself. Gravity waves are a problem simply because they're really hard to observe. We have spent billions of dollars here in the United States trying to detect them with LIGO, which is a long baseline interferometry system that has multiple setups across the Earth where they have giant, essentially letter L's, different perpendicular tracks that they look for the length of the tracks to change as a gravity wave passes over the planet Earth. The problem is that these setups also detect things like, oh, that mountain actually weighs more because it's absorbed a lot of water from that rainstorm, and there was this small seismic thing. Yeah, we can't do it from the surface.
But the Eddington Eclipse experiment is just like that is, and with relativity, I mean, that is classic, perfect process here, right? That Einstein does the calculations, explains something that was already an anomaly with Mercury, and then makes a prediction about what experimenters should find if they try to do something. And so then the experimenters go out and he says, hey, I know this has never occurred to you, but why don't you go and see if stars are bent by the gravity of the sun? And people are like, what? Okay. And then they go and they see the gravity is bends the light from the sun. And then the prediction holds, and they you couldn't ask for a better scientific theory really than that. And the fact that he then made, he's like a Nostradamus. he made all these predictions about what we should see in the universe, and then the experimenters went out and they were true.
Except you can recreate how he made his predictions. You can't recreate how Nostradamus made his predictions.
Well, sure you can. You just make stuff up and it's all wrong. Right, that's how you do it.
Yeah, then there's nothing the same between those two.
Right. So all I'm saying is that if you are a wannabe physicist, scientist out there, and you want to really perfect your craft and you want to be remembered through history, just be more like Einstein. That's all I'm saying. Right?
And this is where there's so many areas of science where we get questions, and sometimes we have to say, not actually science-y right now. What caused the Big Bang? Don't know. Can't get there from here. Not testable. What is this string theory thing? Don't know. Can't get there from here. Not testable. Give me a theory that has tests, and I will happily read your maths. But if you present me something that has no testability, I'm not sure that's worth my time right now. Life is too short for untestable theories.
Right. Now, were we going to tackle some of the other experiments as part of this? My concern is that this is going to turn into a series that's going to run for 7 years. So, because there's so many great experiments, and we are in the nitty-gritty of how these experiments were set up and how they worked and what the outcome was and how it really helped push the predictions forward. And as you said, there's the time dilation, there's indirect detection of gravitational waves, there's the precession of Mercury, there's all of these other experiments. So
we've already talked about the precession of Mercury in another episode where I got the number wrong. That's why I remember we did it. We are going to hit on some more of these experiments. We're not going to spend 7 years on it, although we could. I had the terrifying realization this morning that I've now been podcasting for more than 10 years. And so clearly we could keep going. But we will be getting back to straight astronomy in the not-too-distant future. I just want to do a little bit more to explore the atom before we get there.
Sure. Why don't we... I don't know. We'll put a limit on the number of these experiments shows we're going to do, and then we'll move on to other topics in space and astronomy because there's other stuff too. But we really want to hear about it.
And the reason that I added this one is we're gearing up in 2017 for an eclipse that's amazingly viewable. The one that Eddington dealt with in 1919. Started over South America, great, wonderful populated cities, but it started there. It didn't have a lot of track over South America. Then it spent a vast amount of time crossing the Atlantic, went over the Principe Islands, went over Africa, but by and large, this wasn't an eclipse that was observed by millions and millions of people. In 2017, we have an eclipse that basically is going on a music tour of the United States, starting at Seattle, crossing through St. Louis, Nashville. Pick a city with a music style you like, go there, watch the eclipse.
Yeah. I will absolutely be visiting the United States during that time period. We're about 900 days away, I think, at this point.
And people are starting to gear up. I'm on a task force with the American Astronomical Society where we're starting to gear up on getting the word out on how to observe it safely. We'll be doing something here. The eclipse is at maximum 30 miles south of where I live. It's going to be a great event, and we're going to be able to, if we feel like it, recreate what Eddington did, except better. And It's always fun to recreate things better.
Yeah, so by all means, absolutely clear your schedule. 2017, August, you're going to want to visit the United States and you're going to want to see this eclipse because it couldn't be a better time of the year. It couldn't be moving through a more easily accessible part of the United States. It's going to be mind-bending.
And every time someone says, "Where's the best place to go?" all I can say is pick the type of music you like and go.
I'm going to look at past weather forecasts and find a place that typically gets a lot of sun during August, but that's just me.
Yeah, it's August. Everyone gets. Yeah,
Yeah,
that's
I
a good
know.
idea, but still.
I was thinking Eastern Oregon.
One of the rainiest places in the U.S.?
Eastern Oregon.
Okay.
Deserts. Yeah.
Oh, right, right. Okay.
Yeah. Cool. Okay, well, thanks, Pamela. We'll see you next week.
Thank you.
Okay, hang tough while we...
I totally forgot that Oregon had deserts. It's tropical rainforest in my head.
Ah, no. Um, no, it's the East is very dry.
Not
Same with
tropical,
Eastern
temperate
Washington.
rainforests.
Yeah, no,
Temperate rainforests.
Eastern Washington, even Eastern British Columbia. Eastern British Columbia is rattlesnakes and tumbleweeds and dust devils
I
when it
had a
never
snake in
rains.
my hotel room on St. Patrick's Day.
What kind of snake?
It was a little corn snake. It decided to slither up the pipes and join us in the bathroom in our hotel room. And
In in
in
Texas?
Texas.
Wow.
And there's something about getting to banish a snake on St. Patrick's Day that brings me great pleasure.
I hope you banished it gently.
I did. I scooped it up into a styrofoam cup. It was too small to actually pick up without being afraid that I was going to hurt it. So it got scooped into a cup and carried out to the grass.
Aw. Okay. Just about ready.
That was utterly random, but it still pleases me greatly.
Okay. And then we don't have a lot of time, but we will take some questions. Okay, so
Lots of
James Gibbs
toes.
says, having witnessed the awesome eclipse here in England on Friday, is just going to view the eclipse in the U.S. in 2017. I will be asking for a refund if it is cloudy. So it all depends. Try and, I guess, maximally, improve your chances of actually seeing the eclipse, or whether you want to hang out with people and try and watch it together. So anywhere in the desert from
I
Eastern
Steve
Oregon through.
Steve Chisnala makes a great comment. He said, "Yeah, Fraser Cain's right, but avoid where the 2017 eclipse pass crosses Tornado Alley." Yeah, that's actually a pretty good idea,
Yeah, good call.
which means avoiding where I live. But
Yeah, I'm not. I'm not getting. Although I'd love to visit and enjoy an eclipse with you, if the math doesn't work, I'm sorry.
I know.
I'm going for the eclipse, not for.
And you also have kids, which means road tripping to Oregon's just easier.
Yeah, absolutely. Peter Lau asks, you may have answered this before, but what event made you want to become science educators? Is there some event, Pamela?
Um, I think it was accidental. When I was growing up in Boston, I was first a student in the MIT Educational Studies program and then a teacher for it. And I realized that it's actually really fun teaching people things. And when I was at Michigan State, I was part of the science theater troupe. Literally, it was a troupe called Science Theater, and we did science demos and blew things up. We were actually the opening act for Michigan Festival one year, and that was kind of cool. And I just didn't quite stop. There's a lot of things in my life where the real answer is I tried something and I never stopped doing it.
Yeah, same for me. I never planned to do this. I think I've always enjoyed explaining things for people, and I've always really enjoyed. There's sort of like if you see that the virtual star party promo, whenever I set up a telescope and there's Saturn, I always want other people to look. I enjoy other people seeing something, experiencing something, learning about something better than almost I enjoy it myself. And so that's sort of one of my greatest joys in life is to just help other people really appreciate things. And so it's just kind of natural. You just sort of end up here. So I can't think of any one moment or event. It's just sort of like clearly the natural calling's been dragging me my whole life. Pull another one. Steve Chisnell says, isn't there a second eclipse due in 2024 with a path crossing the path of the 2017 eclipse? I don't know.
Yes,
Google,
there
help
is.
me out.
They cross in Virginia, one of the Virginias.
Whoa. And that's the place to go. April 8th. So April. So, you know.
That's okay.
Yes. It's going to cross really close to you, I think, actually. Really close.
It's down near Carbondale, but I thought it was along the Virginia border.
No, it's not going anywhere near Virginia. It's going to go right through Indiana, Illinois, Missouri, Arkansas, Oklahoma, Texas. So
The 2024 one?
It's literally going to cross in your backyard. Yeah.
Okay, so then there's another one that crosses in the Virginia area, and I don't remember the year that happens. There's a lot of these, and we're about to get really lucky in the United States, having not been lucky for a long, long time. Oh, Graham Stickings is rubbing it in about the David Tennant, Andy Serkis.
Yes, I have, Graham.
I have not. I can't figure out where to get it. I actually just ordered the BBC Region 2 and will condemn one of my computers to being a Region 2 DVD player.
Yeah. It's available in the UK on DVD. All right. Okay, I think that's all the questions that I've got there. Let me see.
Nancy Graziano is commenting on smashing a watermelon for science. You don't smash watermelons for science. What you do for science is you take a person, you lie them down on a bed of nails. You then take another bed of nails, flip it over on top of them. You then put a cinder block on top of the bed of nails, on top of the person, on top of another bed of nails, and smash the cinder block with a sledgehammer. And they actually don't get harmed. Yeah, there's no harm because of the way momentum works. It's really kind of awesome.
All right, let me see. I'll take some questions here. So this comes from Christian Loveric. What would Jupiter or Saturn, for that matter, look like as if they were as close as Venus?
Bigger. Right. They'd be much brighter in the sky, much bigger in the sky, and I think the bigger would be the coolest part.
Yeah, I mean, you could probably at that point make out the moons of Jupiter, the rings of Saturn with the unaided eye. That'd be amazing.
Yeah.
Okay.
That's going to be a new homework problem, I think. That's a cool question.
Samuel Castillos asks, how can I see Google Earth live with satellite? You can't. So all of the images that you see on Google Earth are not done live. They're done over the last couple of months or even potentially years. They take pictures and they'll task these satellites over time, take a bunch of pictures, upload them all into Google Earth, and so you can actually tell. Like, I can see when the picture was taken because you can spot things that you know are different in your yard. And so, for example, I used to have a little silver car in the yard, and so I could see it in Google Earth, but now it's gone, and so I know that they'll have taken another picture when that silver car is gone. Yeah,
so I laid down brick stonage around our house for the gardens, and you can see that. And then we redid part of our roof, and we're like, no one can see our roof from the street, so the flat part of the roof we just did in white, boring, cheap stuff. It shows up like a helicopter landing pad in Google Maps.
Whoa. I don't know if you know. Okay, here we go. So Shanmugan Anadham asks, what's the meaning of GA and MA in universe formation? For example, the Earth formed 4.6 GA.
So that's
years, right?
Yeah, giga years.
Yeah.
So MA would be mega, so that's billion and million.
Yeah, and it would be annum, I think. So giga annum and mega annum. Annum being Latin for year. So, so if you see GA, that means it was billions of years ago, and if it's MA, it's millions of years ago. Now, but the Europeans do it a little differently, don't they? Don't they say like 1,000 million, as opposed to, all the Europeans are going to be nodding their heads as I say this right now, and feel free to jump in the comments, all of you Europeans who I know are watching. You don't say billion, you say 1,000 million.
I did not know that.
Yeah, and they don't, and then they say, and so then they'll say, like,
See, I'm used to people who say giga years or mega years, kilo
yeah,
years.
yeah,
Because
but it'll be
SI,
like GY or MY, right?
yeah.
Yeah. So anyway, incomprehensibly large amounts of numbers. So there you go. Let's see if I got any more here. Whoa. So here's a question. It comes from Gary Mays. If gravity is energy, then there's a continuous loss of mass by particles.
Gravity isn't energy.
Well, we don't know what gravity isn't electromagnetic energy in the way that magnetism and mass and all that are all the same thing, right?
It's still not an energy. Those aren't an energy either.
No, they fall under the, the theory of electromagnetism and the
Right.
what's it
So
called?
there's
The combination of the forces, right?
right. So all
Simple
four
MC squared.
forces were originally conjoined into a single force. Gravity broke off first. I think the strong force broke off next, the electroweak, and then electromagnetism are still conjoined. But they're four forces, and the force itself, while it can cause things to go into motion, and that motion is associated with an energy, the force is not an energy.
Right. But there's some question whether or not there are particles that communicate gravity back and forth, right? Gravitons.
Right, and those would be massless particles moving at the speed of light.
Right. So gravity is not an energy. You can just you can increase, I guess, the potential energy from gravity by moving something further away from a gravitational object, and then it will convert that potential energy into kinetic energy as the
Right.
thing falls. But you are not. It is not energy. It is just it's gravity.
And well, and the thing is, it's conservation of energy. So I'm looking for something I can drop without doing harm. So I've picked up this bull clip, and I exerted force, burning up chemicals in my body. So I've now taken whatever the heck went into coffee beans and artificial creamer, converted that into. I think that's the first time I've sneezed on air. I've converted coffee beans and creamer, which is the last thing I consumed, into energy necessary to lift the bull clip. So I put energy into this. When I let go, the energy I put into it gets converted into kinetic energy as the gravitational force pulls it down. So all the energy is all the energy is conserved. And in fact, when it hit the ground, you probably heard the noise it made, and that was its energy going into sound, heat loss as it shocked the floor. Energy is not gained or lost except potentially via dark energy, which we don't understand. So I'm just going to ignore it for now.
Mm-hmm. Graham Stickings has mentioned that a UK billion is 10 to the power of 12, which is what I thought. So in other words, a 10 with 12, 1 with 12 zeros after it, which we would call a trillion. In the UK, they call it a billion. Isn't that just madness?
Two countries separated by language that they call the same thing.
Yeah, and so they call it it's a million, right? So their billion is a million, which we would call a trillion. And
Okay.
And so I used to get yelled at whenever I would use the word billion in articles. So they never stopped me. But anyway, let's see. I think we got time for like one more question. Here you go. So Gary Mays asks, if the Big Bang is derived from 4% of the matter of the universe, might there be some errors with the Big Bang theory? Was Einstein wrong?
Well, Einstein didn't come up
I
with the
know.
Big Bang.
I know.
So all of our tests for the Big Bang have so far proven true, and there's uh, fairly large gaps. We don't know what triggered the Big Bang. We're not entirely sure why we have an overabundance of matter compared to antimatter. There's a lot of missing pieces to the Big Bang, but all of the parts of the theory that have been developed and that are testable have all proven true, down to the ratios of specific kinds of atoms, to the rate at which different formations have been seen. It seems to be a solid understanding. It's just an incomplete understanding.
And so this discovery of dark matter doesn't it doesn't change the theory of the Big
No,
Bang.
not
Dark
at all.
matter obeys the Big Bang,
Right.
is expanding outward just like regular matter.
Yes.
There's just more of it out there than anyone had ever thought.
Exactly. The Big Bang actually makes no predictions about how much mass should be in the universe. This is something that when I was an undergraduate, we learned that the density of mass, in that case, we were only talking about luminous mass because we still hadn't fully figured out how to fit in dark matter. Um, Mass, the amount of it would relate to the fate of the universe. Were we going to collapse, stop expanding, expand forever? Finding dark matter and dark energy has just helped us nail down different movable variables in the Big Bang theory.
There you go. Let me take one more because I feel like we're on a roll here. Oh, it's such a long one. Okay, Corey Morgan asks, and I already know the answer to this question, but I'm going to do it anyway. So when a photon travels through space from its source to some target, such as our telescope, does time elapse in the photon's frame of reference? In the case that no time elapses, how does the photon's electromagnetic field oscillate at the frequency corresponding to its color?
Um, in its perspective, no time elapses. Yeah, and
That's my mind being blown.
and the oscillations of its field are separate phenomena.
So what we see from outside the photon is different from what the photon experiences because everything is relative.
Yeah.
And if you're moving at the speed of light, you would get to enjoy no time. Or don't get to enjoy no time because there's no time to enjoy it. So yeah, no, we did an episode of our guide to space on that, and it's a crazy concept to wrap your head around.
Yeah.
And the only thing is that photons aren't people, so they don't experience time anyway. So don't worry about it.
That is a great retort.
Cool. Well, I think we should wrap this up. So thank you, Pamela, as always. Thank you, everyone, for watching. Really appreciate it. We will do this again next week.
We will.
All right. See you guys later.
Bye-bye.